So we're going to look at this idea of self-inductance, which is going to remind ourselves that when we've got a coil of wire and we pass a current through that coil of wire, it sets up a magnetic field around that coil of wire. And so what we're thinking about with inductance is what happens when we switch on and switch off that current, and that magnetic field is set up or collapses. Because we know from Faraday's law that a change in magnetic field is going to lead to a voltage being induced, and so we get these temporary voltages induced across an inductor, both when the current first switches on and when the current switches off. So when the current switches on, initially there's no magnetic field through the inductor, and so when we switch the current on and the current starts to flow, that starts to set up a magnetic field. But because there's no magnetic field already in the coil, a voltage is induced across the coil that opposes that current flow. And so initially when we switch on the voltage across the coil, no current flows because the voltage induced across the coil is equal and opposite to the voltage of the supply. And then as time passes, that current does gradually begin to flow and the magnetic field does gradually begin to get set up, and as time passes the current flow increases and the induced voltage decreases until after a time the induced voltage is not really measurable, it's a negligible induced voltage, and the current flow is not impeded by that at all. And so we can write down this equation here that epsilon is minus L di by dt, so epsilon's the induced voltage across the inductor. Di by dt is the rate of change of current in the inductor. The reason why we get such a big voltage when we first switch that switch on is that to go from 0 to something, that's an infinite change in current. So we can get an infinitely big voltage induced, whatever it needs to be in order to prevent any current from flowing. But then as time passes, that change in current goes from being kind of infinite to measurable, and then we no longer get a voltage that's big enough to oppose the supply voltage. The minus sign is just a consequence of Lenz's law that tells us that the induced voltage is always going to oppose the change in current flow. And the L is the self-inductance, and self-inductance is characteristic of the coil, which tells us how much voltage is induced for a certain change in current. And so and that's to do with how big a magnetic field is set up in the coil. So what factors might that self-inductance depend on?
More wires wrapped around it, maybe?
Yeah, so greater density of coils, so more wires per length. What's the other thing that we can do to a coil to get a much bigger magnetic field from it? Something physical that we can jam into the middle of that hole that's going to make it.
Maybe some iron.
Some iron core. Yes, the presence of an iron core, because an iron core is ferromagnetic, which means that it will amplify the magnetic field, the quite small magnetic field from the current flow, to a much stronger magnetic field, which means we're going to get a much greater induced voltage, because it's going to be a much greater change in flux for each amp per second.
You could put any ferromagnet metal?
Yeah, like nickel, or what's the other one? Cobalt, maybe.
Yeah, cobalt's that one.
Cobalt. Does that make sense for self-inductance? Has anyone got any questions about that?